Okay, I think we're good to get started. Welcome everyone to today's webinar from PacTrans. My name is Cole Kafka. I'm the Assistant Director at PacTrans. We're the Region 10 University Transportation Center funded by U.S. Department of Transportation. Today, it is my pleasure to bring you research results from a project that we funded several years ago on connected technology and winter weather. Before we get started, I just wanted to let everyone know that this is being recorded and at the probably within the next day or so, we will post the recording on our YouTube channel and on this project's project profile on our website, the link for which I will put in the chat in a moment. And you'll also be able to find it if you subscribe to our newsletter. So the other thing I wanted to mention briefly is for those who haven't spent a lot of time on Zoom, we have the Q&A box enabled. So if you hover your cursor over your screen, you'll see the Q&A icon at the bottom of the screen. When you click that, it'll open a box for you. You can put your questions there. You can leave questions as the presentation goes on, but we probably won't get to them until the end. You can also see other people's questions, and if you see one you like, you can hit the thumbs up on it. It will upvote it, and it will prioritize the questions based on questions that are most liked, so that we make sure we get to the ones that most people want to hear from today. And I think that's it. So with that, I'd like to introduce today's presenters. The first presenter will be Dr. Xianming he is a professor of civil and environmental engineering at Washington State University, and the founding director of the National Center for Transportation Infrastructure, Durability, and Life Extension. He has served as the site director for 2 Tier 1 UTCs, CESTIC and CAMSE. Dr. Xi is a fellow of ASCE and the editor-in-chief for Springer National Journal, Journal of Infrastructure, Preservation, and Resilience. 2 of his projects won the AASHTO High Value Research Project Award in the last 5 years. He won the Leon Luck Outstanding Faculty Award by the WSU Department of Civil and Environmental Engineering in 2018. And one of his papers won Best Paper from the ASCE Journal of Cold Regions and Engineering in 2012. Our second presenter today is Dr. Zion Pooh. Dr. Pooh joined Monash University as a lecturer in October of last year. Prior to joining Monash University, he was a research associate in the Civil and Environmental Engineering Department at the University of Washington. His active research fields include intelligent transportation systems, connected and autonomous vehicles, Internet of Things, urban computing, and transportation data science. He's published over 30 peer-reviewed journal articles in IEEE Transactions on Intelligent Transportation Systems, IEEE Internet of Things Journal, Transportation Part C, Journal of Intelligent Transportation Systems, and others. So with that, I'm going to turn it over to Dr. Xi, and he can get started. So if you want to share your screen, and I will bow out.
Thank you, and let me share screen. Not sure why it's not shared. Okay, here we go. Thank you, everyone, for joining us. And again, I'll present the first 20 minutes or so, and then Dr. Pooh will present the rest. First of all, I would like to thank PacTrans and Washington State DOT for the financial support. I also appreciate another Tier 1 UTC, CAMSE, for funding part of my time. And also we thank the professionals who respond to our survey, the company who lended us the sensor, and also Professor Yinghai Wang was one of the PIs of this multi-institutional project. And we thank other visiting scholars of UW contributing to this work. And what I present today will be actually published as a paper in Journal of Cold Regions Engineering. First of all, why do we care? First, you look at the global situation, up to 50% of the northern hemisphere is snow covered in winter, as shown on the left, bottom left. On top of that, when you look at climate change and weather anomalies, they do affect snow cover distribution, duration, and amount. When it comes to surface transportation systems, then that could translate to risks to driving public. So in the United States, according to the Federal Highway Administration, more than 70% of the roads and 70% of the population are located in snowy regions, as you can see in the map in the middle. The area in the blue circles are considered as snowy regions. So each year, the highway department spend approximately $2.3 billion fighting snow and ice to make the roads safe and drivable. And the indirect cost in terms of damage to the infrastructure of such operations is another $5 billion. And the surface transportation system is vulnerable to extreme weather events. As we know, recent years have seen increased frequency and intensity of such events, and that further adds to the challenge. So to mitigate the negative effects of winter weather, winter road maintenance operations are essential for safety and mobility of the driver and public. In the toolbox of the transportation departments, there are different practices such as anti-icing, de-icing, plowing, and sanding to provide a reasonable level of service under winter weather, especially with some of the newer practices or more effective practices such as anti-icing. They tend to be more proactive and rely heavily on accurate, timely, and reliable road weather information. And if we do it right at the right time, the right location, then we can use less salt or less abrasives, and therefore the operations can be more reliable and resource efficient and more environmentally sustainable. Because recent years have also seen increasing concerns over the potential risks to infrastructure, to motor vehicles, and to natural environment. And a case study of Utah Department of Transportation we conducted a number of years ago found out by increasing the usage and improving the accuracy of weather information, we could significantly reduce the winter road maintenance costs. Well, that also translates to less salt use and less damage to the environment and infrastructure. So in that context, connected vehicle technologies hold great promise because this presents an opportunity to vastly increase the spatial and temporal resolution of road weather data. When I talk about connected vehicle, I'm not necessarily referring to autonomous vehicles, even though, as we know, autonomous vehicles are connected, but not all the connected vehicles are autonomous. So just make an distinction there. Anyways, the CV technologies enable mobile data collection and supplement the present capabilities of road sensing. Currently, mostly we're relying on things like road weather information system or hours stations. Those are typically at only a limited number of fixed locations. And also CVs would enable better response to changing conditions and improve efficiency and effectiveness of the operations. In Europe, there's a project, European Y-Safe Car project, already explored the use of V2V and V2I technologies, vehicle-to-vehicle and vehicle-to-infrastructure technologies. There's also the V2X, basically vehicle to everything, vehicle talking to everything else, pedestrian or other devices. And the Federal Highway Administration in the United States already developed this architecture reference for cooperative and intelligent transportation, which defines how CVs would be beneficial to a variety of service programs, including road weather applications. When we look into recent initiatives or programs in the last decade or so, maybe decade or two, you can see there are a number of efforts to use advanced technologies or intelligent transportation system technologies to improve safety and mobility on the roadways. And I don't want to get into every one of these, but just so you know, these are not necessarily sequential because they do overlap in time. What's interesting is prior to the idea of connected vehicle technology, there were a number of smart snowplow technologies or maintenance decision support system software applications trying to basically achieve better mobility in the winter time. And then when you look at more recent, there are more pilot testing, like in Tampa, Florida, in New York City, and in Wyoming, where they're dealing with like high wind scenarios or intersection safety issues, using connected vehicle technology as an enabling technology. And then most recently, the Federal Highway Administration, sorry, there's a typo there, FHWA, developed this Weather Savvy Roads program. Basically has two modules. One is Pathfinder, which works for the traveling public or travelers. And the other one is IMO, integrating mobile observations, which aim to help agencies to deal with weather response. The challenge is that all of these technologies or initiatives are still in the infancy, or in terms of being in the planning or pilot testing stages. So few of them are specific geared towards improving winter road services. What's interesting is also, in addition to connected vehicles, one would argue that both physical and digital infrastructure should be upgraded to take advantage of the emerging technologies so that we can facilitate better integration of vehicle and infrastructure, or the term could be VII, vehicle infrastructure integration, and to enable better decision-making of various users across various stakeholder groups. And this was a commentary I published last year to look at that issue. But today's talk is truly on connected vehicles. So let's switch gears back to CV. To understand, what the highway departments think of CVs in terms of helping their operations or providing better service, we conducted a national survey of transportation departments across North America. As you can see, the map highlights where our responses came from. 51 effective responses from winter road maintenance professionals. And right now, we'll look at how they collect road weather data. Mostly, as you can see, is always road weather information system stations and cameras and manual patrol. So these are not really effective, and they are really costly and provide really low resolution, spatial resolution, as well as temporal resolution. And then when we ask them how do they anticipate the usefulness of CV weather data, most people think it's at least moderately useful or even extremely useful. And also we asked them to rank different scenarios where they could potentially incorporate the traditional hours data, which is a limited number of fixed locations, with the personal connected vehicle data or mobile plow data, which will be across the entire roadway network. As you can see, most of them think, such integration would really benefit like the traveler information and advisory, and benefit the road surface condition reporting, enhanced decisions related to how we do anti-icing or de-icing or other operations, and how do we do better job with proactive maintenance and provide a better level of service. And on the other hand, most agencies anticipate that such integration will be really difficult. There are also two main concerns we identified, one of which was how CV would perform, as part of the system under poor weather conditions, because both the physical and digital infrastructure might become vulnerable under extreme winter conditions. The other one is really security. System security from hackers is another major concern. So in light of the published literature and also the national survey results, we developed this concept operations in terms of how CV applications would benefit winter road services. So as you can see on the left, now in addition to the traditional road weather information system, we have connected vehicles on the entire roadway network, and they could be sending data to roadside unit, where the roadside unit further interact with so-called ancillary equipment, which are the road weather, hour station sensors or cameras or other detectors and also intact with the data analytical center where the data is being quality controlled, and the algorithms or models are used to derive alerts and advisories, and those are further sent to either the road maintenance department or the traffic management center, or TMC, and then through which they can send some information for traveler information purposes, such as user interfaces like 511 system or highway radio or websites or your phone apps. So in such a proposed system, we basically have 4 different subsystems for information collection, processing, communication, and distribution. Again, if you're interested, you can read the paper, but or our final report. But basically, I want to talk a little bit about the information processing. As you can see from roadside units and the ancillary equipment, the data is being fed into the module to process, and then for quality control analysis, and then you move on to the risk assessment module where algorithms or models are used, and then it's fed into alert module. So what's unique about this concept is that, first of all, we propose to deploy multi-access edge calculation at roadside units. Traditionally, all the data are sent to the central cloud computing, which causes challenges for data storage or delay. Another thing is that we propose to customize the information for users. For different user groups, then you have different type of alerts or information service, so that would better meet the diversified demands and enhance the user's trust and willingness to participate. Because in addition to the connected snowplows, we need personal vehicles to be more connected, and so that we can achieve a higher level of market penetration for CVs. So with the CVs coming in the near future, we can anticipate the benefits, such as people are able to make better trip plans. We can also enhance the efficiency of maintenance departments. As I mentioned earlier, we probably can use less salt and leave behind less footprint. And also we can enable better maintenance strategies and reduce materials and costs. So there are some limitations, however, in this concept. First of all, we need enough roadside units and enough CVs, right? So when we talk about the density of the units or the market penetration of CVs. Also, with the increasing tremendous amount of data available in real time, you basically pose a challenge for the server capability and performance. Also, the transmission becomes a challenge because you do need encryption technology and other firewall technologies to make sure it's secure, away from the hacker attacks. And also user interface will be critical to convey the message without distracting the driver, for instance. To conclude my section, basically winter road condition assessment using severe technology has been demonstrated and will likely be widely implemented by DOTs for mostly 2 reasons. One, better decision-making for winter road maintenance. The other is really providing better travel information and advisories. And also, there has been very limited development or pilot testing of CV applications designed for improved winter travel. And we can see that DOTs are still a little bit worried about integration of CV with hours and system performance, privacy, safety, driver distraction, and the cost. And the concept, again, is to collect the mobile road weather information from CVs and through controlled area network and the AV automatic vehicle location and vehicle mounted sensors. And then these data, excuse me, will be coupled with the point data from hours and the cameras and enable better decision making. Also would benefit the TMC travel alerts and advisories. Thank you for listening, and I welcome your questions. Dr. Pooh?
Yes, let me share my screen. Okay, so thanks for Professor Xianming's presentation, and also thanks for Cole's introduction of me. So basically, in Dr. Shi's presentation, so he basically introduced how we can utilize connected vehicle technology for improving traffic safety and mobility. But in my presentation, I will mainly focus on a specific numeric forecasting algorithm, like about road weather condition prediction. So in this slide, there are two figures show like two severe traffic crashes caused by inclement road weather. And you can directly observe how much we lost in these two crashes. Lots of vehicles got damaged in the crash, and probably we have got lost in the crashes. So actually we have like 1 million vehicles crashes occur each year caused by adverse weather in the United States, and we have 800,000 injuries, 6,000 and 6,000 fatalities in these crashes. Approximately, we need to spend $42 billion for covering the cost of the injuries and the loss of life and property damages from weather-related crashes. And we as Professor Shi's introduction, so we still have lots of other statistics that can prove inclement road weather is a notable inducement of traffic crashes. And most of countries spend considerable resources for solving the traffic problems caused by adverse weather. But however, sometimes we do face problems for building a perfect winter road maintenance strategy. For example, the information is not enough for us to know when the road weather will become worse for driving, and which part of the road segment needs maintenance activities, and how much we need to spend for addressing road weather issues. And sometimes we only have very short time period to respond to the inclement road weather. So in order to have the real-time information of the road weather, the Department of Transportation employs road weather information station for acquiring information to support road maintenance activities. And however, due to the cost and other considerations, we cannot build the information station everywhere. The coverage of the information system is limited, and only a few part of the road segment can be monitored by road weather information station. And in order to widen the monitoring range of the information station, like people build a road weather model for estimating road weather condition in the places where we even don't have road weather measurements, but we have some air weather condition data that we can use for the estimation. So how we can have better data which cover the most of road segments without newly building any infrastructures or facilities. As Dr. Shi introduced, CV technologies provide a promising solution for us. And we also have like several novel sensing devices that enable vehicles to be a strong mobile sensing stations. Like the bottom figure shows road condition monitor, which is a novel sensing device called road condition monitor 411, and which is an optical sensor that we can easily install to a passenger vehicle. And the existing researchers conducted experiments to demonstrate that the RCM 411 is accurate in temperature, water thickness, and road surface state condition detection. And even for the road friction detection, which is one of the most difficult sensing tasks in road weather monitoring, this sensor also can get the actual friction value based on calibration methods. So as I mentioned, sometimes we have too short time period to respond the inclement road weather. So if we can have accurate predictive road weather information, the winter road maintenance will become more efficient. As the aforementioned considerations certainly motivated us to conduct this research, and our research purpose is to develop a road weather condition prediction model utilizing connected vehicle data. And also the purpose of the research include accommodating other problems with road weather prediction, such as dealing with missing values in the dataset, and also setting the hyperparameters of the prediction model. So we built a two-step method for road weather prediction. The first step is road segmentation. So when a vehicle which equipped with sensing device drive through a specific corridor, we will have road weather measurements for each road section along this corridor. And generally, the adjacent road segments share similar properties, but the distant sections tend to be different for each other. So the road segmentation is to guarantee that only one road weather condition exists within each road section. And we utilize this k-means clustering algorithm for road segmentation. And after segmenting the whole road into multiple road sections, in the next step, the road weather prediction will be conducted for each road section independently. So previously, several literatures demonstrate the time series features of the formation of ice on road. So this road weather forecasting problems become a time series prediction problem. So if we have one measurement of road weather of a specific location per day, after several days, we probably can forecast the road weather in the future based on the measurements in previous days. And like seen from all the time series prediction model, long short-term memory neural network is one of the most popular one, and characterizing by the capability of handling not only the short-term time series features, but also long-term patterns. Scholars have demonstrated its superiority in forecasting tasks. And in this study, we utilized Lstm as the prediction algorithm for road weather prediction. And these two figures shows the framework of the Lstm. And basically, the input of the algorithm is a vector of road weather measurements. And each element of the vector would be 1 day measurement. The output is the predictive road weather information in the next time step. And due to time limit, I won't go into the detail of the algorithm structure. So if you are interested in the algorithm, please check out our publications on the Journal of Intelligent Transportation Systems. So we did design several experiments to validate our proposed algorithm. We collect the data which from an open source website provided by the RCM company, and data was collected by one RCM sensor from main corridor in Finland, which is called E75. And the RCM sensor was installed on a maintenance truck, and the truck drove through the testing field at least once per day. So finally, we got a data set with with more than 1 year data from 2017 to 2018. And those two figures shows the statistical description of the data set. The right top figure shows the box plot of road surface friction versus road surface condition, and it is obviously the road surface friction decreased when the road surface condition got worse, and after the road segmentation step, we got more than 1,000 road section of this whole road. And the bottom figure shows time series patterns for 5 randomly selected road segments, and they share a similar time series trend in this data set. And as usual, we divided the data set into training and testing data set, and we did select some baseline models, including feed-forward neural network, support vector machine, random forest, which are popular machine learning algorithms people often used in their research in prediction. And this table shows the comparison results, and the metrics are calculated based on the predictive performance for all road sections. Based on the results, our proposed Lstm-based prediction algorithm outperformed all baseline models, and so all 3 metrics are lower than those of others. In the bottom figure, we present the predictive performance for the whole corridor. And most of prediction are close to the ground truth. Only a few of them have a little bit difference, so which also demonstrate the accuracy of the prediction. So we also investigate the impacts of several hyperparameters on the predictive performance, including the number of time lags, the interval between time steps, and additional inputs of the model. So and finally, we got the most precise prediction when the number of time lags equals to 7, and when the predicting time interval become larger, the prediction accuracy decreases. And so it's also interesting for additional inputs of the algorithm. The predictive performance of the Lstm was improved by adding road surface water thickness as the additional input of the model, which is shown in the bottom table. However, when road surface water thickness and the road surface temperature were added at the same time as the additional input of the model, the predictive performance become worse than we only taking road surface condition as the input. You can see like when we only have a road surface condition, the accuracy is about 50%. The error is about 50%. But by adding water thickness, the accuracy improve a little bit. And but we add another variable, the road surface temperature, the accuracy become worse. So the reason could be the additional temperature related features made the Lstm too complicated, and also brought lots of useless information to the Lstm model. So for developing an Lstm algorithm, we need a set of time series data. And for each two adjacent time steps, the time interval should be the same. So if we have some missing values or data quality issues, the data set cannot be used for algorithm development. So based on our observation, the road weather data which we have do contain lots of missing values. And by searching the literature, there are lots of reasons could cause missing values in the data set. For example, not always we have maintenance vehicles available, and the economic labor cost issues, and also the problems with sensors or data transmissions. So in order to accommodate the missing values issue, we developed this masking mechanism for capturing the masking at time interval of the input observations. So usually the input would be only one vector, which only contain the road weather measurements. But with this masking mechanism, in the equation at bottom of this slide, well, X is a length times series measurement with 3 missing values at time step 3, 4, and 7. And S is the vector denote the time step when measurement is observed. So which means X1 is measured at time step 0, and X2 is observed at time step 2. So M is the vector representing the missing status, which there's 3 missing values is marked in 0. And the delta denote the time interval between adjacent time steps. Then the input data of the modified algorithm is formatted as this, and the algorithm would know the missing value information in the data set. So the gated recurrent unit, which is the simple version of Lstm, which has more efficient ability for computation. And we also deploy 2 decay rates in the unit to handle the missing values. And the decay rates are learned from the training data. The exponential negative rectifier is deployed to keep the decay rate in a range between 0 to 1. We utilize a data set with 20% missing values for the algorithm validation. And we also select 3 simple data imputation methods as the baseline data imputation method for the comparison. We're combining several other machine learning algorithms with the baseline data imputation method for demonstrating the performance of our proposed GRUD algorithm. And since both short-term features and empirical average values were considered in the decay mechanism, the proposed GRUD outperformed all baseline models. The results are shown in these 2 figures. And we also investigate the impacts of the amount of missing values on the predictive performance. So for this experiment, the input data sets with the missing value, missing rate from 0% to 50% were used for testing. And so based on the results, as the missing rate increased at the bottom figure, the prediction precision gradually dropped. So, and it is noticed that stopping the stopping distance of vehicles and the driver reaction time have a non-linear negative correlation curve with zero surface friction. So 0.1 error in zero surface condition prediction could cause tens of meters error in stopping distance. Thus, even the proposed GRUD networks is capable to handle the missing values. The impact become more considerable when the missing rate getting larger. And so in the top right figure, we also visualize the decay rate. The decay rate is trained by the real data, which can demonstrate how the informative missing patterns were utilized for missing value imputation. And according to the figure, the learned input decay rate range from 0.8 to 0.2, and decay rate dropped with a large slope when the time interval is smaller than 1 day, shown here, and then the decline rate of the input decay rate decreased, and finally it become constant when the time interval is larger than 20 days. So we also demonstrate our proposed method in Washington State. So we installed 2 RCM 411 sensors on the maintenance truck, which drove through the corridor shown in this figure once per day. And there is a phone put in the vehicle, which is connected with the RCM sensor, and data is transmitted to the phone through Bluetooth, and then it will send to our remote server through the cellular network. We utilize the DriveNet system as a data analysis and visualization platform, and which is originally established by the startup at the UW for lots of big data implementations in transportation engineering. And Watchdog also employ this DriveNet system as one of the main tool for traffic data analysis in Washington State. So recently, I noticed that the 4th edition of the DriveNet just released several weeks ago. If you are interested, you can check it out through this link. And for our implementation, we also embedded the proposed prediction algorithm in the DriveNet system. Once the system receiving the data from RCM 411 sensor, it will match the sensor data with the on the spatial map, and then the data will be transitioning to the Lstm module for generating the prediction results, and the final step would be the data visualization. This is the platform of our visualization tool, and the road is marked in different color based on the predictive road weather condition. And the user also can select a specific date to request the prediction results. So basically in our research, we demonstrate the benefits of connected vehicle data for improving winter road safety and mobility. And during the research, we also identify several future research directions. Like in our research, we only utilize this connected vehicle data, but still have lots of very valuable resources that we did not use, like the data collected by road weather information station. So how to integrating this several data sources, especially for dealing with missing values in the data set, would be one of the future research direction. And also, we only can predict the future road weather condition, but but what is the risk level based on the predictive road weather? Is still unclear. So another future direction will be identifying risk level based on the predictive road weather condition. So finally, I want to just thanks for the support from Professor Xianming Shi and Professor Yinghai Wang. They provide lots of suggestions and support for our research. And also thanks for Watchdog providing testbed facilities and resources. Without that, we cannot just build up the testbed to demonstrate our proposed systems. And also many thanks for the assistance from the business scholars, Ms. Shuo Wang, Mr. Jingyang Li, and Mr. Chenlong Liu. And based on our research, we published 2 journal articles. One of them published on Journal of Intelligent Transportation Systems. Another one published on IET, Intelligent Transport Systems. So if you are interested in our research, you can just feel free to check it out online. Thanks for your attention. I think that's pretty much from me, and I'm very open for suggestions and questions. Thank you.
Great, thank you both very much for that. We do have a number of questions, so let's get right into them. The first question was posed pretty early on, I think, Dr. Shi, at the end of your presentation. If calculations done at the roadside unit, then there's no in the loop for humans for data quality and verification.
Right. That's an interesting question. Basically, what we propose is really the edge computing, or so-called multi-access edge computing, or MEC, which is a different kind of network architecture. I mean, compared with traditional, cloud computing. So really, in terms of quality control, security, first, quality control is no different than the cloud computing. It's basically just allowing the computing to occur at the edge of the network so that you have ultra low latency, say 5 milliseconds with today's technology. AT&T and others are kind of leaders in that. Basically, whether or not a human will be involved in the quality control, that's a good question. I think even if you do cloud computing, mostly the quality control is done by algorithms and models, not by human nowadays, because just tremendous amount of data at real time. It's just nearly impossible to use a human to decide whether the quality is good or bad. I mean, that's where the machine learning and other things will become, the more practical approach. I hope that sort of clarifies a little bit. But again, the benefit of edge computing is really to reduce the need for sending the data to a remote data center, and therefore you have a much higher level of security and much faster response.
Great. I know we had one question that kind of got answered in the chat, but for those who are watching this recording after the fact, so this is kind of a 2-part question. The first part is whether or not this work could also work in the summer as opposed to just in the winter. And then the second part of this person's question pertains to differences in the effects of snow versus heavy rain on the CV technologies.
Right. Yeah, even though we heavily focus, this project was designed to focus on snow and ice because this kind of conditions present a large challenge for our region at least. But yes, supposedly the open architecture or the concept of operations would be useful for other types of weather-related mobility or safety issues. like heavy rain, you do have some potential visibility challenges, and by having more CVs on the road and being utilized in the network, then we can definitely improve the temporal resolution and spatial resolution of the data, and therefore enable better decision making.
Great. This next question, is anyone studying using CV data, specifically roadway traction data, to automatically implement traffic signal progression speed changes? It is pretty simple to detect vehicles slowing for bad conditions, but once slowed, along with the progression speed of the signals, it would seem harder to detect whether roadway surface improves and can support higher speeds. CV traction information could help. I'm sure that's not that simple once you get into it. So if somebody is studying it, maybe you could get that funded.
Well, I know Ziyuan probably will be more qualified to answer this, but my take on this is the idea is basically along the same line with weather responsive traffic control. Yeah, doing it in real time, of course, you run some tremendous risk, right? So I think as an additional data source, I mean, CVs can definitely improve weather responsive traffic control, but in terms of how to do it or how to make sure you balance performance with risk, I mean, Ziyuan, probably you can comment on that. It's probably not that easy, right?
I think, but this is a good idea, but it's probably not that easy. So I read some articles previously, but I will explore this direction in the future. Probably we can develop proposals, probably will found it.
Yeah, somehow the voice quality from your end is not that great. So, but I agree with you. Weather responsive traffic control is an interesting area. Again, with the increased amount and resolution of the data, every aspect of operation would be improved. But yeah, it takes more research to make it practical. Nice, interesting idea. Yes.
Great. We have another question. Thanks for the presentation. You showed that upon the inclusion of surface temperature as an input variable into the model, its accuracy decreases. Could that be because of issues in the training phase? The addition of more input variables should either improve the performance of the model or show insignificant effects. Dr. Pooh, I think
I
was...
will answer this question. So certainly the additional, you guys hear me clearly?
No, you're still kind of bouncing in and out.
Yeah, I don't know what's going on, but I would say while you're trying to figure it out, I try to kind of chime in. There are several possibilities, right? One possibility could be the quality of the pavement temperature data itself could compromise the model. But of course, yeah, with another possibility is really like how you train it. I guess for practical reasons, if you add another parameter and you don't see improvement, you just don't want to pursue it too much. I don't know. Hopefully that clarify. But yeah, it's kind of strange. I was hoping like adding another parameter would help. But maybe you can type your response in the chat box, and then,
it looks like he's typing it right now. We apologize for that, everyone. But that should be visible as a type.
Yes, sorry about that. Can you hear me clearly for now? What about my voice quality?
It's a little bit better.
Not good. Okay, yeah. I will try to answer this question. So for the additional input, certainly traditionally we would have better performance, but if the additional variable does not have a high correlation with the target prediction output, it will like bring lots of more complexity to the model, and then the weights, some of the weights will be become useless for the prediction. So the prediction will be like decrease in terms of the performance of the prediction. So before you decide to adding the additional input, you need to maybe do some preliminary analysis about the correlation between each other. Yeah.
Right. We had another thought that actually came through the Q&A box. Someone suggested that the temperature data could perhaps be confusing the algorithm because frequently it has to warm up to snow. So under very cold conditions, tractions could be surprisingly good. So perhaps the issue is that there's kind of something underlying that's kind of unforeseen there.
Yeah, I was also thinking, you know, in some temperature windows, you actually end up with the need to apply either abrasives or de-iso or anti-iso. Maybe that will totally throw off some of the friction numbers. I don't know. Yeah, it's just too complex.
Great. Okay, we've got just a few minutes left. Does anyone else have any last minute questions for our presenters today? And I guess as in case someone's typing out a last minute question, I'll just take a moment to re-announce that this presentation has been recorded and it will be published on the PacTrans YouTube channel in the coming days. So if you want to go back and revisit things, or if you want to share this with someone who you think would be interested in it, we will make this publicly available shortly. And I also dropped into the chat earlier a link to this project's profile page on the PacTrans website, where this recording will also eventually get posted. And for those who just recently joined, I will drop it back in the chat right now. It does not look like we have any more questions, so I think with that we can conclude for the day. Dr. Xu, Dr. Pooh, thank you so much for your time and the excellent presentation. Attendees, thanks for joining. I hope you learned something from it, and stay tuned. PacTrans will have more such webinars in the future.
Thank you, Cole. Thank you, everybody.
Thank you. Thank
Thanks.
you, everybody.
Bye, everyone.
Bye.